Okay, I'm going to call this chapter 19, part 3. I'm trying to prevent the video from becoming too long, right? I think chapter 19, part 1 was too long for one video. Okay, so for this part here, we're talking about the standard reduction potential. We're talking about how this table came about. We know that from the table, and I found this online. This title here is missing a very important term. It's the standard reduction potential table for all of these half reactions, right? And it was measured in standard conditions. And it's telling you for these half reactions, the amount of electricity released. This slide here is giving you the backstory of how these half reactions were measured. And it starts by saying the absolute tendency of a half reaction standard reduction potential cannot be measured. Okay, that's translation for if you want to measure this potential for the half reaction of fluorine molecule becoming fluoride ion, you can't measure that by itself. From the name of the half reaction is only half of the whole. Okay, so if you want to measure this number here, you really have to pair it with another half reaction. Let's see where they say that. Only the potentials relative to another half reaction can be measured. Yeah, that's what they're saying. You really have to pair the half reaction with another half reaction, then you get whole because two halves make a whole. So they say here, to overcome this limitation, a standard half reaction for the reduction of hydrogen ion to hydrogen molecule is selected and assigned the potential difference of 0. Okay? So not only is it assigned a potential difference of 0, it is given a unique name called the standard hydrogen electrode or She electrode. I like to call it She. Okay. Standard hydrogen electrode or She electrode. What does that mean? I'm going to stick with the explanation provided by this book so it's not confusing. In getting all of these numbers here, the standard hydrogen electrode, She electrode here, I tried to draw it earlier and I was taking too long drawing it. It just takes too long. It's too much. So I want to draw it here. What I'm going to do is you know what I can do? I can copy it over. There are times when I forget like the power I have with technology. So here we have our standard hydrogen electrode, right? Let me copy it. Can I copy it? Yes. Younger me than me a few minutes ago. Paste. No. Let me go back. How do I go back? Go back. Paste image. Much better. Much better. Okay, let me make this image bigger. So instead of me trying to draw this complicated picture, which I tried to, my picture was horrible. Let me just make this. So we're going to call this will be our cathode. Oops, I'm done copying. This would be our cathode. Okay. So the She in this case was assigned as the cathode. Okay. This is where the wire comes in. This was paired against anodes, right? And so I'm going to let me select one of these here. I don't want to go from iron to iron because that gets more complicated. I want to go from a solid. So I'm going to use a gas. Let me use a metal. Let me do PD. Ooh, palladium. Ooh, nice. So we're going to be dealing with palladium right here. So that will be palladium metal, PD, solid. And then in solution, we have palladium ion. So PD 2 plus. Okay. And so the palladium is placed right here, and we can see here as the reaction proceeds, the palladium is assigned 0.915 volts. So what you're saying here in the slide is the standard hydrogen electrode is assumed to contribute nothing at all to the voltage. It is assumed to be 0. In that case, whatever number is seen here is assigned to palladium alone, not palladium and hydrogen, because how do you divide it between the two? You can't divide it in half. And we can't make this, to make things less complicated, we can't make this X and then subtract. And chemists are like, listen, we just need a relative value and we can move on. We can survive just fine with a relative value. So let's make this 0 volts and then move on. It makes our lives easier, okay? Whatever number we see here, when the half reaction in this table is paired with standard hydrogen electrode or She, will be assigned to that half reaction, to this. It will be because of this, not that. Because we assume this is contributing, this is 0, right? So for this one here, for example, the palladium, we would actually see a negative 0.915 volts. So why did I make this negative? You see how this plays out. Because the number we're seeing here is technically not just from palladium, it's from the combination of the two, right? And so the number we see here is the E standard of the cell. Let me show you how it plays out. We mentioned before that the standard potential of the cell is equal to the standard potential of the cathode minus that of the anode, right? We said the cathode is 0 volts. The anode, we don't know what this is. Let's call this X because we're solving for it. And the cell came out to be negative 0.915 volts. Okay? And so when we work this out, we end up with, this is 0 volts. So just negative X equal, I should write my X like this, be consistent. Negative 0.915 volts divide by negative 1, divide by negative 1, and we end up with what? The potential of the anode, which is lead and lead 2 plus, is equal to 0.915 volts, okay? And so you can see this is how they got the number. Even though we assigned the whole thing to be negative, that's how we get the number for palladium, okay? Now, what does that mean? For those of you who are working this out in the lab, I will explain to you in the lab that when you, based on the positions we have here, and I'm about to get to that, but I may as well tell you guys what, since we're here and it relates to this. You see that the elements on the top of the standard reduction potential not only have a positive potential, but it's the highest positive potential. And as you go down, the amount decreases and decreases and decreases and all the way until it gets to 0. And 0 is where hydrogen is, the one that's the standard. And then in this one here, it continues on the right side, right? Yeah, it continues here. Then you have the negative one, starting with hydrogen, you have the negative ones, negative, negative, negative. And then it gets a bigger negative as we go down, all the way to the highest possible negative one, okay? So what do the positives here indicate? Let's start back with a picture. When the E of the cell is negative, that just means that the assigned roles here in the setup do not match the preferred roles, okay? In this table, the standard reduction potential table, what you're seeing is the preferred roles of the half reactions. So apparently these half reactions have a preferred role. I see this table here almost like, I used to watch movies back in the days where kids in high school or whatever in school will audition for a play, and then some will get the roles they wanted, some won't. And then the ones who got the roles they wanted, they were happy. Yeah, we got the roles we wanted. Yeah, they'll be happy walking away. I wanted to be a princess, and look, I'm a princess. And then somebody else wanted to be a prince, and then they made them a page boy. Like, I wanted to be a prince, but no, I became a page boy. So when people didn't get the roles they wanted, they were usually sad. They kind of had a negative attitude. Those that got the roles they wanted were happy and had a positive attitude, right? So you ask yourself, how is a movie that's a generic movie I just described go with this? Okay, it's a complicated backstory, a little bit complicated. This table is all about standard reduction. That part is very important, potential. So the theme obeyed in this table is reduction. How do I know that? In reduction reactions, electrons are added. I'm going to skim through this very quickly. See, all of these electrons are reactants, not products. So these are all written in a reduction format. You have to notice that. Reduction, all of these are reduction. Even the ones on the right, these are all reduction right here. They're all reduction. But since redox indicates some are reduction, some are oxidation, so then how do we know what is actually reduction in this table and what's oxidation? The half reactions that prefer reductions are pro-reductions, and they're all positive. So these up here that really want to be reduction, because they want a reduction and they got reduction, of course the attitude is like, yes, I got what I wanted, right? So they're all produce a positive potential, to me, it's like a positive response because they got what they wanted. They're all written in the format they like. Yes, yes, yes. When you're going up the table, you're getting more yes. I know I'm playing too much, y'all. I'm trying to make this interesting as much as I can. The happier or the more the half reaction wants to be reduced, the further up it is in the table. The one that doesn't want to be reduced as much is further down. So you can say here confidently, palladium wants to be reduced, but not as much as fluorine. Have you seen fluorine's numbers? 2.87. Fluorine really wants to be reduced, while palladium wants to be reduced, but not as much as fluorine. Okay. Same thing with gold and lead. Gold wants to be reduced more than lead 4 plus does. Okay. Same thing with cerium, same thing with chlorine. The ones that are further down, though they're both positive, want to be reduced less than the ones that are further up. Okay. And then, of course, hydrogen is somewhat indifferent. It's a 0. And then when we move on to the right side in this case here, or further down the chart, the ones that are negative, they're not happy with the role they got. They were assigned reduction. They're like, this is not the life I wanted. I didn't choose this. I wanted to be oxidized. These are like, no, negative attitude, and even bigger negative response, right? They're like, no, we don't want to be reduced. We really prefer oxidation. How do we know that from the table? Because of the negative voltage. So these really prefer oxidation, okay? What does it have to do with the E of the cell? You ask. Everything. The overall, remember, the half reaction is negative if the assigned role is opposite to that which is expected. We're trying to connect expectation with, or preference with assigned, right? Does the assigned match preference? Ooh, okay, let me move this over. That's the big question here. Does the assigned role equal preferred role? Okay. Of course, you can see for all of the negative ones here, they want to be oxidized. Lithium wants to be oxidized the most. How do we know? Big negative number, like really protesting. I don't want to be reduced. I really want to be oxidized. I want the flip of this reaction, not the way the reaction is written. I want the reverse. Okay. So when we look at this number here, because the overall cell potential is negative, the assigned roles here are not what they wanted. Really, palladium wanted to be here, and then relatively, she wanted to be here. If you flip these roles, you get a positive number. So once again, we're seeing that we can tell that this wants to be reduced more than standard hydrogen electrode. How do we know that? When it was given the oxidizing role, it produced a negative response. Negative, okay? Let's go ahead and move on because we'll talk about this again and again. The standard reduction potential is defined to be exactly 0. Therefore, standard reduction potentials compare the tendency for a particular reduction half reaction to occur relative to hydrogen, right? If this chemical here wants to be reduced more than hydrogen and you place it in the oxidizing position, you will get a negative result, right? But if you place it in the desired position, which is the reducing position, you get a positive result. So in this case here, assigned role right now is not equal to preferred role. If you flip it, then it will be equal, and then this part here will end up being positive, right? Anyway, hopefully that wasn't too confusing. We'll make sense of it some more later on, but let's go ahead and move on. So the half reaction with a stronger tendency toward reduction than standard hydrogen electron have a positive value of E reduction. This is referring not to the experiment, but to the table. So all the ones that have a positive potential right here that end up being positive, right? These tend to be, they want to be more reduced than hydrogen. So we have to cover that. Then half reaction with stronger tendency towards oxidation than she have a negative value for E reduction, okay? Okay. I think I defined this earlier saying for an oxidation reduction, when you have a anode, this is equal to negative E of cathode, right? So I mentioned that earlier, so we can move on from here. So with that being the case, we've talked about which way electrons will flow. I've already mentioned that. I can move on. Yay. All the information I gave you guys before kind of helps us, right? Now we're finally at the table, and I can write on this table. So remember, with this value here being the highest, F2 wants to be reduced or undergo reduction. Okay, so to pick up where I left off, fluorine really wants to be reduced, right? So the further up the half reaction is, the more it wants to be reduced. Okay. And then the further down, the more it wants to be oxidized. Now remember, okay, I was trying to figure out what was I trying to share. Remember, the element that is either wants to be reduced or undergoing reaction tends to be, so in this case, the way you describe it, don't say fluoride. We're assuming that we're looking at the forward reaction. So the description will be about fluorine. So F2 is the one that is undergoing reduction. Okay. The element undergoing reduction is also a great oxidizing agent. So you can see right here, the one undergoing reduction is also a stronger oxidizing agent. And they're telling you why it's a stronger oxidizing agent is also a weaker reducing agent. I feel like these are all relative terms, right? Okay, so for this part here, we're going to talk about how to read this information here. So like, give me just a moment. Okay, so I'm trying to make sure this is not confusing because some of the questions are a little bit finicky, so you have to really know what's going on. When it comes to describing this reaction, you have the reactants and this is the product. Now you can see over here in my table, it's a one-way reaction. In this table here, it's a two-way reaction. I'm trying to be less confusing as possible. We're usually looking at the forward reaction, okay? So in the forward reaction, this is the reactant of focus. So F2 wants to undergo reduction. Undergo reduction. So F2 wants to undergo reduction. Okay. You would say that way versus describing it from the point of view of F minus, because this reaction is the one that is positive, right? The forward reaction, with this being the reactant here, is the one that's positive. And remember, the element that undergoes reduction, so F2 that undergoes reduction, is also a strong, since it undergoes strong reduction, is a strong oxidizing agent. Because I told you guys in class, the one that undergoes reduction is also an oxidizing agent. It causes oxidation in the other element, right? Strong reduction, strong oxidizing agent. So you see that label right here. Now, these are all relative terms. So the one that's a strong oxidizing agent is a weaker reducing agent, okay? Now, on the other end of this table, here's a weird thing. They don't write the reaction, or they don't describe this reaction starting from left to right, since it has a negative potential. This is the part where you have to flip this, make this positive 3.04, and flip the reaction, do the reverse reaction, right? I know, it's a weird thing. So Li solid breaking down to Li positive plus E negative. Then you would say lithium solid prefers oxidation, because you're talking about something positive, something that's happening that's related to the positive value, right? Prefers oxidation. For that reason, lithium solid, stronger reducing agent, right? So when you're writing it, you're going to write it as lithium solid prefers oxidation, not lithium ion, but lithium solid, because this is actually showing you the oxidation reaction. So lithium solid prefers oxidation, therefore it's a strong reducing agent. It'll be a weak oxidizing agent. It acts better as a reducing agent, and is a strong one because it prefers strong oxidation, right? And that's how you would describe that. Okay, I've seen some questions where they're trying to make sure you really understand what's going on, and the answer choices will be which one prefers oxidation, lithium ion or lithium solid, and you're like, wait, what? Yeah, it's kind of tricky. because in the oxidation reaction of lithium, the beginning, the reactant is lithium solid, not lithium ion. Lithium ion cannot, well, I should say cannot be oxidized further, but it's usually not oxidized further. What I'm trying to say is lithium ion doesn't become lithium ion 2 plus like that. No. Usually lithium ion, the reaction it will normally have will be to take an electron to become lithium solid, right? That's reduction if it adds to an electron. So bottom line, just hear me out. Bottom line, lithium solid is the one that is trying to get oxidized to become lithium ion. Okay, and that's how you read this. So once we understand that, we can now move on, right? Let's go ahead and move on and finish up this chapter. So wow, it shows me I'm on slide 50, just slide 50. I've already described this part here. Yeah, I have described this part here, so I'm not going to repeat that part. The most powerful reducing agent is lithium. I already described that. You see how they say it here? Lithium solid is the one that wants to be oxidized, and therefore, because it wants to be oxidized, it's a powerful reducing agent. Lithium solid prefers oxidation to form lithium ion. You see what I'm telling you right now? And then the weakest reducing agent is fluoride. And fluoride does not prefer to be oxidized to form F2. The most powerful oxidizing agent is F2. F2 prefers reduction to form F minus. So let's go back to this part here so we can see. Okay. So the reactant that we're focusing on here is F2 forming F minus, and that is reduction. So that's the one that produces the stronger oxidizing agent, but the reverse will, of course, not be preferred. It's the forward reaction that's preferred. And then this one here is the reverse reaction that's preferred. Hopefully that's making sense. Then here, the most powerful oxidizing agent is F2. F2 prefers reduction to form F minus. And then we have the least powerful oxidizing agent is Li plus, and Li plus does not prefer to be reduced to form Li solid, like I explained before. So I'm going to move on from here. Okay. I've already given you guys this part here. Now, this is a caveat. Because cell potentials are intensive properties, you cannot double or triple them, even though the doubling and tripling is required to balance the equation. Do not multiply these numbers here, the potential, by coefficients because you're trying to balance the equation, okay? Because cell potentials are intensive, when determining the cell potential, do not multiply the half cell reaction by the potential values or the EMF values. So when you're trying to balance this equation, do not try to modify the potentials of the half reaction. Even if we are multiplying the half reaction by a factor to balance the electrons, do not multiply these values here. Okay, this makes it easy. Copy as is. Okay, let's go ahead and move on. Now, we already mentioned before for the E of the cell, the potential of the cell at standard conditions. Take the potential of the cathode at standard conditions minus the potential of the anode at standard conditions. We can do that, right? Here's a simple one. Simple one. Oh, before, this is a little bit more complicated. I just said simple and I was like, yeah, this is not simple. Remember the one I gave you guys earlier, the example we had here? Let's figure out its cell potential. So our cathode here, the cathode, E standard of the cell, our cathode is what? Copper, right? Let me use this one here on the right to find copper. Where is the copper? Copper. I'm going to pretend I have no idea what this is. There is copper with 2 electrons. Oh, you have to make sure it matches, right? Not necessarily the format, but it has to match. You have an ion here, you have an ion. 2 electrons, 2 electrons. Copper is solid, it's implied. 0.34 volts. This one here is 0.34 volts. So my E of the cell, this is a cathode, right? 0.34 volts minus the anode. I need zinc solid. I don't see zinc here. Let me go to the right, I have the zinc. There's zinc sulfide, but I don't see zinc. Oh, there is zinc with 2 electrons. What's the number for zinc? Negative 0.76. This is negative 0.76. So minus negative 0.76. So we end up with 0.34 volts plus 0.76. I end up getting what? 1.10 volts, right? This is what I got earlier, right? Okay, so while we're here, I need to mention something about spontaneity. So we have just learned that if the cell potential is positive, that's a spontaneous reaction. So if E of the cell is positive, that's equals to a spontaneous reaction. Spontaneous. Okay. Use tabulated standard electrode potentials to calculate the standard cell potential for this reaction occurring in an electrochemical cell at 25 degrees Celsius. The equation is balanced. Okay, so we're being told ahead of time the equation is balanced, right? So we can be aware of that. But we may still have to balance the equation. So to work this out, what you want to do is I copy the reaction over again. This is younger me, so I didn't have to recopy it today. You want to identify what is being oxidized, what's being reduced. So you can separate the whole reaction into two halves. This is the overall reaction. Technically, this is overall. But you want to know what's the oxidation part, so what's the reduction part. Because I can tell you this, if you try to find this overall reaction here, you shouldn't find it because this table is full of halves, not wholes. So if you find, okay, you see there's aluminum here, but not one added to nitrate. Let me look for nitrate, nitrogen, not here. Let me go to the left. Oh, I have a nitrate here, but it doesn't have, and it has an OH. That's not the right one I'm looking for. And then this one has an NO2. That's not it. Let me keep going. This may not be the best. I don't know. It's kind of hard to get a really good table, right? Because I don't even think I have what we're looking for. But let's see. I really think the one that came with this textbook is really good. It has the ones that we're needing, right? Because I have a nitrate here, but it doesn't have the right products. We need 2 waters, not 2 OH. Yikes. The point I was trying to make, though, wasn't about that. I was trying to tell you that we have to use the table that came with the PowerPoint, not this one here. Okay, so I tend to go for the oxidation reactions first, and I have it written here, so I'm going to write that first because it tends to be the easier one to identify. Aluminum becoming aluminum plus. Oxidation number for aluminum based on the rules is 0. This one here is +3, right? Because you have an element with nothing else attached to it, so it's going to be 0. The charge here is +3, so oxidation number is +3. Okay, I'm going to assign oxidation numbers here. This is +1. And then oxidation number here for oxygen is, I'm going to just show you the process, right? It's H2O assigned from right to left. Each oxygen is -2. Each hydrogen is +1, +1, +1. These add up to +2. This adds up to -2. The overall compound is 0 because there's nothing written up here, right? The 0 is implied. So I'm going to write the oxidation number for each individual element, not the group as a whole. So +1 for hydrogen. Okay, let me do the same thing as I figure out oxidation numbers for the elements in the compound. So for NO, I'm assigning from right to left, right? Correct? There is no number here, so the overall charge is 0. The oxygen is normally -2 because that's the charge, right? Oxidation number is -2. So the amount that nitrogen has to be, so we can add to oxygen to get 0, will be +2. So the nitrogen here is +2, right? The oxygen is -2, and together they make up together they make up 0. Now for this part here. So you assign oxidation numbers for all of the elements to identify what is what. Actually, for this part here, I just realized something. I don't need to keep going because I don't need all the information here. All I need to know is what's oxidation, what's reduction. So for oxidation here, all I need is Al solid producing Al3 plus. It's implied that if this is my oxidation part picked out, then whatever is left behind here will be reduction. So I can make this here NO3 minus plus 4H plus. Yeah, I can just keep it that simple. And this NO, yeah, I was getting caught up in trying to figure out all that stuff. No, all we need to do here is just to identify the half reactions, right? 2H2O liquid. Okay, so now I have to complete the top half reaction, right? You can tell here, because of space, I'm going to write this up here. There is no charge on the left side for aluminum, so that's going to be 0. I'll leave it as is. On the right side, there's 3 positive charge from aluminum here. So I have plus 1, 2, 3. To make the right side match the left, I need to add 3 negative. You see that? So this can cancel out that, this can cancel out that, this can cancel out that. That way on the right side, I have no net charge like I have on the left side. So I'm going to add 3 electrons here. Okay. Now let's go ahead and look at this part right here. On the left side, I have one negative charge here. Here it says 4 positives, right? That's how you read it, as 4 positive. So 1, 2, 3, 4, okay? The negative from here cancels out one of the positives from here. So I'm left with 3 positives. I need to add 3 negatives so that each of these can come and cancel this out, right? And then this can match that side. So plus 3 electrons. I'm trying to erase this without creating commotion. Okay. So now we cancel out the electrons here and we have our overall. But before I do that, I need this electrons here. Hold on a second. Before I cancel this out, let me go ahead and pull up that table. Oh, I wish I had the table on the side, but this table is all convoluted. Okay, let's find aluminum. You know what? We can find the aluminum here, right? The aluminum shows up over here. There it is, Al plus 3 electrons. That's negative 1.66 volts. I wish this one was here. This one was here, but it's not. I'm looking for an NO3 plus 4H. Let me go back to the table, the big table. There. NO3 plus 4H plus 3 electrons. It's not in the same order, but we need this number here, 0.96. Copy it as is. Don't flip it. Just copy it as is. So 0.96 volts. Okay. So to get the overall reaction, we have to add these two together, right? This and this cancels out. We don't need the numbers anymore. So we get Al solid plus NO3 negative plus 4H plus AQ to give us Al3 plus AQ plus NOG plus 2H2OL. Okay. Ooh, let me see that. Can I decrease the size of this a little bit? Okay, let's go back to this. So E naught of the cell is equal to, the cathode is this one here. This is cathode. This is anode. 0.96 volts minus negative 1.66 volts. 0.96 minus negative 1.66. We get 2.62 volts, okay? 2.62 volts. Okay, oops, I wrote this higher. I should write it here. 2.62 volts. This is a spontaneous reaction. Why? Because E of the cell is positive. Okay. Yeah, so they set it up like that. They separate the two. You have that, and we got this number here. We can celebrate. Woohoo! Confetti, confetti. Yeah. So I already worked on this before, right? Now, remember in the previous chapter, it was mentioned that spontaneity is directional. So if we decide that the forward reaction stated here is a spontaneous reaction, If you reverse this, in other words, you assign the one that prefers oxidation a reduction role and vice versa, you will get a non-spontaneous reaction. When the E of the cell is positive, the redox reaction is spontaneous because delta G will be negative. Okay. So we can see here with this one here being positive, this one here wants to really be reduced because it's positive, it's further up. This is negative, this one really wants to be oxidized. When you're given those roles, then you end up having a spontaneous reaction. So let's see what happened here. Since Cu becoming Cu2 plus is oxidizing, and then Zn2 plus becoming Zn0 is reducing, if you look at this one here, the reason why it ended up being a non-spontaneous reaction, assigned roles are not equal. In the balanced equation, assigned roles are not equal to preferred roles. When paired together, copper wants to be the one reduced, and then zinc wants to be the one oxidized. Over here, copper was oxidized and zinc was reduced. You can see these ones here don't match, and that's why you have a non-spontaneous reaction. Okay, so I'm going to attempt this question right here. Without calculating the E of the cell, predict whether each of these redox reactions is spontaneous when the reactants and the products are in their standard states. If the reaction is spontaneous as written, make a sketch of the electrochemical cell in which the reaction could occur. If the reaction is not spontaneous as written, write an equation for the direction in which the spontaneous reaction occurs and sketch the corresponding electrochemical cell. In your sketch, make sure to label the anode, which should be drawn on the left, and the cathode. Sorry, the anode should be drawn on the left, the cathode, and the direction of the electron flow. Okay, so I'm starting with the first one. I kind of started this, and this is my second take. Okay, so I already assigned oxidation numbers to know what's going on. The iron is becoming iron 2 plus, so that's undergoing oxidation. Magnesium is becoming magnesium ion is becoming magnesium solid, so that's reduction. Okay, so let's go ahead and start from here. I encounter magnesium first, right? Magnesium is in the bottom, so let me go ahead and erase this. I see magnesium plus 2 electrons on the bottom. And then when I scroll up, what am I looking for? Iron. There's iron. Iron 2 plus 2 electrons. So the given roles here for magnesium, for iron 2 plus, the given role is oxidation. Oh, and then for magnesium, the given role is reduction. But according to the table, the one that's further up prefers reduction, and the one that's further down prefers oxidation. So what we're actually seeing is the opposite, right? The given role in A is oxidation, and then of course you have reduction here. So if you look at that, we have a mismatch. Assigned roles are oxidation and reduction. Oxidation for iron and then reduction for magnesium, and then the preferred roles is reduction. So I'm writing that here so we can see there's a mismatch. So bottom line, we can say assigned role is not equal to preferred role. I think it's 2R, right? With iron being relatively higher than magnesium, iron prefers reduction. But in this case here, they were given oxidation. So with that being the case, if you flip this reaction, you can actually get it to be spontaneous. Okay, so let's see what they have here. Yeah, this is currently oxidation. This is reduction right here. But if you flip the reaction, then you can actually get, with this one here being reduction, and then this one here being oxidation, then you get a positive potential. Okay, so the forward reaction as written, this is not spontaneous. I see. This is not spontaneous because we see that the preferred role is the opposite. Is opposite from.
Something went wrong. Please try again.
Okay, sorry. The preferred role is opposite from the given role. Okay. Preferred role is opposite from the assigned role. Okay. So if you reverse this, then you get a spontaneous reaction. The way this is written initially is non-spontaneous. Right here, this is non-spontaneous. Okay. So this one here, non-spontaneous. The forward reaction is not spontaneous. But if you reverse it, make these the reactants and that the product, it will work out. So once again, if you reverse it so it looks like that, this one here is the one that creates non-spontaneous, right? When you reverse it, make the iron reduction and then the magnesium oxidation. This works. This yields a spontaneous. Why? Because iron ends up being on the top and then magnesium on the bottom, which matches what was in the table, right? Magnesium was in the bottom of iron too. Okay, so this one here will yield a spontaneous reaction. So for the most part, in this question here, the goal is to try to create a setup where you can get an overall E of the cell as a positive number. So goal to get the E standard of the cell to be positive. And to do that, you have to give half cell reactions preferred roles. If you give the chemicals the roles they prefer that matches with this table, you will get the reward, which would be the E of the cell being positive. Okay? Okay, now of course it says we should draw this. We're not going to do all that. What's the second half of this question? And the second half of this question was oh yeah, they did it here. So we're just going to take credit for what they did, right? When you switch this around and you make this reduction, yes, and then make magnesium oxidation, that should work. Okay, so let's go ahead and look at. There were two questions, right? This is just answering A. What about B? What was B talking about? Okay, B was talking about iron and lead. Let me go ahead and copy this over so we can go ahead and unpack this in the next slide. Okay, so for this one here, let's look at this. We have iron. We have iron becoming iron 2 plus. This is oxidation, right? Going from 0 to plus 2. And then we have plus 2 going to 0. And this would be reduction right here. So we have an oxidation and reduction. These are the assigned roles. Do these match the preferred roles? So let's go over here and look at iron. Let's find iron 2 plus. With iron 2 plus right here, you're seeing, okay, let me make sure I haven't encountered lead yet. I'm seeing iron 2 plus first. So iron 2 plus 2 electrons to give us iron. Then let me scroll and find lead. Where is lead? Oh, there's lead. So Pb2 plus 2 electrons to give us Pb. Okay, so the preferred roles are, when these are paired together, lead prefers to be the one undergoing reduction, and then iron prefers to be the one undergoing oxidation. Are those the assigned roles? Yes, iron underwent oxidation, so this is check. And then lead reduction, check. But in this case here, of course, you're seeing that these match. So in this case, assigned roles in the balanced equation, right, matches preferred. So I say in balanced equation, matches preferred role in table, the reduction table. For that reason, this should be naturally spontaneous. Anyway, so this one should work like this. It should be spontaneous. We don't have to reverse it. The reverse will actually be non-spontaneous, right? And so this one here should work out. Of course, when you draw the picture, that works out too. And then in the picture, let's see. Iron will be oxidizing on the left side, and then we have lead on the right side. Let me see how we can modify this in a lazy way. Iron will be on the left side, right? So iron will be like that, Fe, then lead will be on the right side, Pb, and then you can have all the components and so on and so forth. I want to go ahead and move on, right? And talk about this part here. Now we're moving on and summarizing how we identify spontaneity. So we're picking up from chapter 18 and combining with chapter 19 to say when you're looking at all of these together, now over here, oh yeah, I gave you guys a summary. When can we tell a reaction is spontaneous? This is how we'll tell. The more common one is delta G. This is the most common. When delta G of a reaction is negative at standard state, we know it is spontaneous. When E of the cell is positive, it's also spontaneous. When K equilibrium is positive, the reaction is spontaneous. When delta S of the universe is positive, the reaction is spontaneous. This tells you how we get delta S of the universe by knowing delta S of the system plus delta S of the surrounding. With this part here to be spontaneous at all conditions, delta H has to be negative and delta S has to be positive, okay? So now we have talked about 5 different ways in which we can use data to decide a reaction is spontaneous or not by looking at some of these values, right? And the question may give you just the first one, delta G, or E of the cell, or K equilibrium, or delta S of the universe, or delta H combined with delta S, okay? So now we're looking at the relationship between E of the cell, delta G, and then K. We have a relationship here that tells you delta G from the previous chapter is equal to negative RT ln of K. In this chapter, we're told delta G is also equal to negative NFE of the cell. When you combine equation 1 and 2, we get the third equation that relates to E of the cell with K, which it says E of the cell is equal to 0.0592 over N log K. So the log natural somehow became log K. So give me just a moment. Okay, so once we have these formulas here, we're going to be using these formulas to solve problems, okay? Let's go ahead and move on from here. So we're told values here. In order for us to use this equation here, we have to know what N is. N is the number of moles of electrons. It's not that simple. N is the number of moles of electrons when they're made equal for each half reaction, when they're made equal, right? And you're about to cancel them out. That's the N we want here. And then F is Faraday's constant, and the value here is 96485 coulombs per mole of electrons. Sometimes it's abbreviated as 96500 coulombs per mole of electrons. Okay, let's go ahead and continue where we left off. Okay, so here we're trying to relate delta G to E of the cell. It says uses tabulated electrode potential to calculate the G for the reaction. So here we have this. So what is E of the cell? Or how do we figure this out? I guess I already copied this here, and I wrote here that delta G is equal to negative NFE of the cell. We know E of the cell is cathode minus anode, right? So let's identify what's the cathode, what's the anode in this reaction. Let's go ahead and assign oxidation states. This is 0 because it's a free element. This is 0. This here is also 0, right? This is negative 1, and this here is negative 1. So looking at the changes from I goes from 0 to negative 1, that looks like, oops, overshot, reduction. From Br negative 1 to 0, that's becoming more positive, looks like an oxidation. So you see how I have reduction first? I'm going to write I2 solid plus, oh no, sorry. I2 solid yields 2I negative AQ. I hope I'm writing too close, right? Let me move this over because I feel like I wrote too close to the right side. There, okay? For this one here, I'm gonna write 2Br minus AQ to give me Br2 liquid, okay? And then, so we have our half cell reactions. We want to get the numbers, right? Oh, let me go ahead and add the electrons. Over here, since I have two minus, I technically have two negative here, right? So to even this out, I want to add two negative here because there's nothing right now on the left side. That will be plus two electrons. Remember, in reduction, electrons are reactants. In oxidation, electrons are products. So let's see how that plays out. On the Br minus, I have two negative here, and there's nothing on the right, so I have to add two negative here to even this out, and now I have two electrons. This is just guiding us visually to know where the electrons go. Hold on a second. Let me erase this first, and then I'll go ahead and add what's missing. Okay, now I'm going to add here Br. Okay, so the half reactions are balanced. Now I'm going to add these to get the overall reaction. So I have I2 solid plus Br negative aqueous to give me 2I negative aqueous plus Br2 liquid. Okay. Let's do it I2 negative. Let's look at I2 negative, I2 negative. Oh, I need the number from here. I'm like, where do I look again? Let me see if I can find it here. I negative. Do I see BR here? BR. Nope. The non-metals tend to be on top of hydrogen. So I'm just taking it slow so that we can look for these together. Oh, there's I2, 0.54, 0.54 volts, right? And then let's look for BR. There's BR, 1.09, 1.09 volts. Okay. Yeah. So now that we got these, let's go ahead and continue from here. This is our cathode, this is our anode. So we have 0.54 volts minus 1.09 volts. I wrote this weird. 0.54 minus 1.09 negative 0.55 volts. I'll tell you right now, not spontaneous. Before we continue, right? What do they want us to do? They want us to find, oh, okay, is the reaction spontaneous or under the standard conditions? Okay, currently, conclusion, not spontaneous. But I think we're supposed to find delta G, right? To calculate the G of the reaction. Okay, so we're not done. We have the E of the cell. So, oh, from this right here, number of electrons are 2, right? So we have 2 moles of electrons. To do an inventory, we have N, we have F. F is a constant, it's Faraday's constant. This is the value right here. We have E of the cell. We just got that, right? Our N is going to be 2 moles electron times Faraday's constant, 96485 coulombs. Oh, I shouldn't, yeah, that's right. Over moles of electron times the E of the cell will be negative 0.55 volts. The volts is the same thing as joules per coulomb. So negative and negative here make positive. So our delta G is going to be a positive number, right? So I'm going to make it 2 times 96485 times 0.55. I get 106,133.5. This is going to be joules, right? So it's going to be divided by 1,000, 106 kilojoules, if you want to run it up like that. Okay, so they made it real, yeah, they really abbreviated this and they wrote it in scientific notation as 1.1 times 10 power 5 when you start from here, right? 1, 2, 3, 4, 5 joules. if you write it in joules, but of course in kilojoules it'll be more like this. Or I guess you can write it as 110 kilojoules. Okay? Yeah. Anyway, this is what they get. This is what we get. So we can now move on. We're not doing any extras. We're just doing the minimum, the bare minimum. Okay. Moving on to this problem right here. It says, refer to tabulated electrical potential to calculate K for the oxidation of copper by hydrogen ion. So we're looking at copper undergoing oxidation, right? This is obviously undergoing reduction. So let's see how this plays out. You can tell here what's undergoing oxidation is copper. What's undergoing reduction is hydrogen. And this is the equation we're using, right? Because that's what works out. Are we looking for a K? Yes. Calculate K. So we're looking for K. This number here has been simplified. We need to get the number of electrons required to balance the equation. Then we need to get the E of the cell. So once we can calculate this and this, we can then find log K. Let's set it up. So we have, I guess I'll start with the reduction first. We'll have 2H plus aqueous giving us H2 gas, right? We know the potential of this is equal to 0.0 volts. And this is the reduction. We have copper solid to give us copper 2 plus. Okay. Before we find what's going on with this, I just knew the hydrogen had 0 volts because it's a She, right? Standard hydrogen electrode. Okay, let's go ahead and add the electrons. Remember, for the reduction, the electrons are added to the reactant side. So you can see right here, we have 2 positives. And there's nothing on the right side. To make the left side match the right side, you add 2 negatives, right? The negatives will cancel out the positives, so we add 2 electrons here. Okay, if you're looking at this right here, the right side has got 2 positives. Add 2 negatives here to make this match the left side, so the negatives will cancel out the positives. We have 2 electrons here. Okay, let's look at our equation and see how this works out. Okay, for copper, our voltage is what? 0.34. It's going to be 0.34 volts. Oh, let me erase this. So I have aqueous here. Okay, let's see. So over here, what do we have? This is our cathode, right? This is our anode. So for our potential, we have cathode, which is 0.0 volts minus anode, 0.34. So we should get 0.34 volts total. And then the number of moles is 2 moles of electrons. Our overall reaction is what? 2H plus AQ plus copper solid. I'm just consolidating all the formulas on the left. On the right side, I'm adding the H2 gas to copper 2 plus aqueous. Okay. And this ends up being negative 0.34 volts based on what we had here. This is supposed to be negative 0.34 volts, right? Okay, so we have the E of the cell. That should be negative 0.34 volts equal 0.0592 volts over 2. This is the moles of electrons, and then log K. So can we solve for log K? Let's see. I'm going to divide this part here, right? We can leave out the units. So I'm going to have 0.0592 divided by 2. That gives us 0.0296 log K. And then we have negative 0.34 divided by 0.34 negative. And do the inverse. Okay, so when I divide this by 0.0296 divided by 0.0296. This is 9. I divide this part, I get negative 11.49 equal log K. To get rid of the log, do the 10 power log K, 10 power this number. This cancels out and we get K equal 10 power negative 11.49. Let me see if I can get the 10 power 10 power the answer. How do I set it up over here in my calculator? Okay, so I'm right here. K is equal to, when I set this up, I get 3.31 times 10 power negative 12. Okay. Make sure you work it out and you get this answer. Let's see what they got, because I got 3.31 times 10 power negative 12. Okay. I guess if you round it up, you get 3.3 times 10 power negative 12, right? You round this up to two significant figures. Okay. Yeah. So let's see. I feel like we're making progress, y'all. We're making progress towards the end of this chapter and trying to power through. Just get to the end. Okay. So what happens to the measurement that is read, the potential, the cell potential? Because remember, the E of the cell potential at standard conditions, is based on the choice of the anode chemical and then the cathode chemical, right? So if we want, and the one of the applications of the voltaic cells are in batteries. What if we want a more powerful battery, the one with the greater volts? What can we do to accomplish that? We can use non-standard conditions, right? So you can see here that the potentials we're getting so far, the cell potentials, these are being measured at standard conditions. In non-standard conditions, when you change the concentration in both containers, this can yield a greater voltage of the cell. So you're seeing standard conditions, right? These are the same chemicals we started off this lesson with, or this, yeah. These are non-standard conditions where one concentration, at least the oxidation side, got changed from 1 molar and it got more dilute. And then the reduction side became more concentrated, right? Because it was 2 molar versus 0.01 molar. But the change in concentration creates more voltage overall. Okay, so from this relationship here and dealing with non-standard conditions, we're able to figure out non-standard potential of the cell using what is called Nernst equation. So for this part here, go ahead and copy Nernst equation. Now to make our life simpler, kind of like the 5% rules, scientists went ahead and assumed that this reaction was taking place in standard conditions where temperature is 25 degrees Celsius. So that got replaced with temperature, but it was replaced with 298 Kelvin. R was replaced with the molar gas constant, that value right there. And then Faraday's constant being a constant was replaced with this number right here. Then log natural of Q was replaced with log, not log natural. And then the equation was recalculated. So technically this right here, even though it shows log natural, this should be log. I don't know, there's a typo there, but that should be log. Okay, so I'm just mentioning it right now, that should be log. So when we have this right here, go ahead and plug this in and you see how it works out. So we're going to be using this equation right here to figure out the non-standard cell potential. And that's why I was able to add this here, but I cannot change this because it's an image. It's actually log Q. Remember, log Q comes from the equilibrium constant where you're dealing with products over reactants raised to the power of the coefficient. So let's go ahead and set this up. The good thing about this problem here is they actually give you the concentrations that you need for this equation here so you can plug them in there. Let's go ahead and start. We're told what is oxidation, we're told what is reduction, right? Okay, so we're working on this problem here. In this problem, we're told determine the cell potential for the electrochemical cell based on the following two half reactions. Now, the cell potential they're asking for here is calculating E of the cell under non-standard conditions. So for that, you're going to look at this. We have copper solid. It tells you that's the oxidation, right? Giving you copper aqueous. The concentration of copper aqueous is 0.010 molar. And here we're adding 2 electrons. Then on the other side, we have manganate, MnO4, aqueous. And the molarity here is 2 molar plus 4H plus. The molarity here is 1 molar, and this is aqueous, plus 3 electrons to give us MnO2 plus 2 waters. The water is a liquid, the MnO is a solid, so we're going to continue with that. Okay, we have oxidation here, we have a reduction. Now, it looks like the copper is balanced. The electrons in the half reactions are balanced, but we need to make sure the electrons are equal so we can add the overall reaction. Since we have 2 and 3, we're going to multiply the top reaction by 3, the bottom one by 2. So we're going to put here 3, right? 3, change this to 6. The bottom one here, you're going to multiply by 2. So we have 2 here. We have changed this one here to 8. And change this one here to 6. And then here we multiply by 2, right? So by 2, and then change this one here to 4. Okay, so we multiply by 2 throughout. Okay. Now you can see the electrons match, so we can say we have N. Let's find the E of the cell. The E of the cell should be the top reaction, which should be what? It should be 0.34, right? I'll write this here. 0.34 volts. The bottom reaction, we're looking for one that has, can I find that here? No, not the manganate. Let me see. Let me not be quick to judge. I'm looking for manganate. I see Mn here, not Mn. Yeah, the manganate I see here produces OH, not water. So yeah, we cannot have it here. And yeah, this is not it. So this is not gonna work here, right? Oh, let's see what we have here. MnO4 8H plus. That's not it either, because you see the product, that's not it. Man, they almost got me. Not really. That's not it. Okay, let's go ahead and copy the one from the slides. Let's see the slides. MnO4, MnO4. I see MnO4 in this one here. This is not it. This is not it either. I think this is it, right? Yeah, that's it. 1.68. Oh, sorry, you guys can't see this. The 1.68, the one that we had before we doubled this, right? 1.68, that's what we need. So let me scroll this back down. Okay, I need the space here. This is 1.68. This is reduction. This is 0.34 oxidation. Okay, E anode, E cathode. Cathode is 1.68 minus 0.34. I get 1.34 volts. Okay, let me add the 2 half reactions. So I get 3 Cu solid plus 2 MnO4 minus. You're going to consolidate all the reactants, right? So I wrote this down. I wrote that down. Oh, the concentration of this bottom one is 2 molar, right? Plus 8H plus AQ, 1 molar, to give us 3 Cu. I need to shrink this somehow because I'm running out of room. How do I make this smaller? 3 Cu, 2 plus AQ. The amount here is 0.01 molar, right? I need that number. Plus 2MnO2 plus 4H2O, liquid. And this is solid, okay? So the E of the cell standard is 1.34 volts. Excuse my, I'm just running out of room here. I feel like I have a lot of room to write, but I really don't. That's the E of the cell, and this is how I got it. Okay, so what we're looking for is E of the cell under non-standard conditions. So for that, the formula will be E of the cell non-standard is equal to E of the cell standard minus 0.0592 over n log of Q. E of the cells, oh, we just figured this out, right? This number right here. 1.34 volts minus 0.0592 over number of electrons. We got this at what? 6 is what we said. 6 and then log of Q. Oh, I haven't solved for Q yet. Oh, man. Okay, let's use the space right here to find Q. So Q is our products, right? So we have one product here that has the concentration. We have copper, iron, raised to the power 3 divided by manganate, permanganate iron, raised to the power of 2. And then we have the hydrogen ion here, raised to the power of 8. So you want to plug in these numbers given to you, right? For the copper ion is 0.01. This is going to be cubed over permanganate ion is 2 squared. And then the hydrogen ion is 1 power 8. And you want to work this out. So we have 0.01 cubed. This doesn't have a hat. It's weird. Power 3. Okay, so Q is equal to 1, 2, 3, 4, 5, 6. 1 times 10 power negative 6 divided by 4. Right? Divided by 4. So this becomes 2.5 times 10 power negative 7. Okay. So Q becomes 2.5 times 10 power negative 7. Let me take the log of that and see what we get. So the log of this gives me negative 6.6. Okay. So this is essentially here. Do I need space? Oh, I should be good. 1.34 minus 0.0592 over 6. And then the log Q, we already solved for it up here, is log of 2.5 times 10 power negative 7. And that ends up being 1.34 minus 0.0592 over 6 times negative 6.602. Let me go ahead and multiply it by 0.0592. So I'm trying to work this part out here and divide by 6. I'm incorporating this part right here. So I end up with 1.34 minus 0.065. So this becomes plus. Minus and minus becomes plus, right? So 1.34 plus 0.065. 1.34 plus 0.065. And we end up with 1.41 volts. Okay. Let's see what is obtained here. Okay, we got this part here. And we got this part right here. Yeah, whoo. We're told in all electrochemical cells, oxidation occurs at the anode and reduction occurs at the cathode. In voltaic cell, remember we said that in voltaic cells we have spontaneous reactions where E of the cell is positive. The anode is the source of electrons, it's the electron producing site and has a charge that's negative. The cathode draws the electrons and has a charge that's positive. Now we're talking about the other cell, the non-spontaneous one. In electrolytic cells, the E of the cell is negative. Electrons are actually drawn off of the anode, so there must be a place to release the electrons, the positive terminal of the battery. Electrons are forced towards the anodes. And so there must be a source of electrons, the negative terminal of the battery. Okay. So remember, this is when you're given the half reactions the role they do not want, and then you're forcing them. So you're giving something that prefers reduction. You're giving it an oxidation role, and you're forcing it to act in that role. You're not cutting it slack. You're forcing it to act in that role. In this case, you have to use a battery to make that happen. So the positive terminal is attached to the anode. The negative terminal is attached to the cathode. Okay, so what we're seeing here is the voltaic cell on the left versus the electrolytic cell. In the voltaic cell, they're reminding you zinc had the role of the anode, the one that was producing electrons, right? In the voltaic cell, in comparison, copper had the role of the cathode, the one that was accepting electrons. Now we have the opposite being true. In the electrolytic cell, you have the zinc being forced to play the role of the cathode, even though it prefers anode, and then copper being forced to be the anode. So a battery is attached here where the side of the battery attached to the anode is actually the positive end. So the positive end of the battery is attached to the anode, right? And so the anode, this being positive, forces the electrons away from copper. So the positive here has to be more positive, of course, than the copper to draw the electrons away from copper towards the battery, right? And of course, this end of the battery is negative. That's pushing the electrons away from the battery towards the cathode, right? And so we're seeing here that the battery is now creating an external force that is now forcing the electron in a direction that is, I want to say, unnatural. So instead of copper being the cathode like it prefers, it now acts as the anode, a role it doesn't prefer, but this works. And so the electrons are drawn from copper once again, and then they're taken towards the zinc. This becomes the oxidizer, this becomes the reducer, and that's how the reaction proceeds. We wrap this chapter up by talking about electrolysis. So in this part here, we're looking at the application of electrolysis. We're told here electrolysis is the process of using electrical energy to break a compound apart. Electrolysis is done in an electrolytic cell. Electrolytic cells can be used to separate elements from compounds. In this case here, the compound that's actually being used to create elements is water. Water is both the chemical in the cathode and the anode. And you can see right here that the battery is used as the power source to create oxygen, the element, and then hydrogen, the element. So it can be used as a source of finding, or I guess isolating elements from the compound, right? And so this technology here is used to create hydrogen fuel cells that can be used, of course, ultimately to power cars. And I was like, this sounds good, great theoretically. And I like to see this maybe like on TV or something. Me personally, I think I'll opt out because hydrogen and oxygen are both very flammable, and I don't know how I feel. I feel some kind of way about this, right? But anyway, remember here in electrolysis, we don't really have a spontaneous reaction. We have a non-spontaneous reaction. So we're looking at this here, right? That ultimately water is acting both as the anode and the cathode, creating hydrogen gas and oxygen gas, which to me are both very flammable. But anyway, why am I whispering? Anyway, but it is great. Imagine being able to use purified water to essentially power your car. I'm oversimplifying, right? But instead of going to the gas station to buy gas, you just use water. That would be great, right? Okay. Some applications of electrolysis are the following: metal extractions from minerals and purification. So we can use that to isolate the element from a complex compound like minerals. It can be used to produce hydrogen for fuel cells, like we talked about right here. It can be used for metal plating. So we're seeing an example of metal plating or electroplating. In electroplating, the work piece is the cathode. So the piece that you're trying to create is put on the cathode side, because cathode side is where the electrode gets bigger, because that's where things are depositing there. The cations are reduced at the cathode, and the plates plate to the surface of the workpiece. So the workpiece is the ring. This is like a ring right here. So you have the silver, right? Here's the silver solid. This is the electrode that's being dissolved So it's like the silver solid is providing both the electrons and it's providing the ions. So you can see right here, the silver solid provides the ions of silver and the electrons. So it's kind of a neat situation here. This metal, a silver electrode, provides the ions. The ions swim to the cathode side and wait for electrons. The electrons, so the ions and the silver ions and the electrons are actually separated, right? With the electrons flowing through the wire, oops, because they're drawn by the battery. They flow through the wire all the way here, and then they sit on the surface of the ring. So the electrons are perched right here. They were together here, silver ion and electrons. They're separated. The ions are drawn to the ring, around the ring, not on the ring, just around here. The ions right here, silver ions. And then the electrons flow out of the solution via the wire and then go and sit on the surface of the metal piece. That's essentially, I call it the ring because it looks like a ring. So as the silver ion sees the electron, it's drawn to the electron and deposits on the ring. Before long, you have little deposits and then you have the ring completely coated by the silver. Of course, they make it look pretty when it's done, right? But you see the tiny pieces of silver. So it doesn't look as lumpy looking like our experimental results or the picture they showed in the beginning. They will smooth it to make sure it's nice and pretty, right? But yeah. And so this electrode here is providing both the silver ion and the electrons that will be used to coat the ring. And most of the time, a more attractive metal, a more valuable metal is used to coat a less attractive but more durable. Okay. Okay. Let's go ahead and look at what we're going to be looking at. So we're going to be looking at stoichiometry with electrolysis. Before we start, we want to remember something. 1 ampere is equal to 1 coulomb per second. And then we said for Faraday's constant, we have 96485 coulombs per moles of electron. No, what else? I think that should be it, right? Conceptual plan. Most of these questions will give you time in seconds. If not, if it's an hour, convert to seconds to start your conversion and then go in order until you get to the grams of metal. Okay, let's go ahead and start this problem out. Do I have a place to work this out? No, I don't. Okay, I'm going to start with a half reaction. Our half reaction is gold. Is this a reduction half reaction? Okay, so gold with 3 positive charge is gaining 3 electrons to form gold solid. So this is the formation of gold solid on some kind of, I'm assuming it's a ring. Gold can be plated out of a solution containing gold ions according to the half reaction. Okay, what mass of gold in grams? So what is wanted here is an amount in grams of gold. It's plated by a 25-minute flow of 5.5 amperes current. So a given time, 25-minute flow of a current, that's 5.5 amperes. Okay, so we have a current. We know Faraday's constant is 96485 coulombs per mole of electrons. And we're asked to figure out the amount of gold in grams. What else are we given? Is that it? Okay, let's figure this out. We'll start with a time. We're given time in 25 minutes, but we need time really as seconds. So let's see. I'll start it like this. 25 minutes is the time. I'll convert the minute to seconds, right? 1 minute is 60 seconds. So I use this time here and we start it in seconds. And then we want to convert the amperes, the current, into coulombs per second. So 5.5 amperes is the same thing as 5.5 coulombs per 1 second. Okay, so what I have here is, I'm going to now copy the 5.5 amperes here. This is going to be 1 second and then 5.5 coulombs. I see. Okay. So now we have coulombs. Now I'm going to use Faraday's constant because I have coulombs here. The number down here has to have coulombs. And that number will be 96485. So 96485 coulombs over 1 mole of electron. That cancels out. So I've used all my numbers so far. Remember dimension analysis from 1411? Our goal is to make sure that you're canceling out the units you don't want, which is what I did here with the minute, right? Cancel the minute out because it doesn't appear in our final answer. Set up your conversions to cancel out all the units that do not appear in your final answer. In the process, you want to introduce units that are getting you closer to the final unit or desired unit, right? So now here we are at moles of electron. We can now deal with the balanced equation. The coefficient we have here is molar amount. So essentially we have 3 moles of electron. And this goes with 1 mole of gold. So I'm going to put here 3 moles electron goes with 1 mole of gold. And over here we have 1 mole of gold goes with, what's the amount of gold? 197 grams of gold. And what was wanted, remember, was grams of gold. So our conversion setup is done. Ooh, am I excited about being done with this chapter? Moles of electron, moles of electrons, moles of gold, moles of gold. And when you work this out, you should get your answer in grams of gold, okay? So I'm going to multiply all the top numbers, 25 times 60 times 5.5 times 197 divided by 96485 divided by 3. I get, I get 5.61 grams of gold. Okay. So from this, we get 5.6 grams of gold, and that should be the amount of gold produced. 5.6 grams of gold. And with that, this chapter is finally done.